In this problem, we have two cylinders, A and C. The mass of cylinder C is given 40 kilogram. The two cylinders are connected through cables and pulley. So we have several cables connected by the ring at point E, and we also have a pulley, a frictionless pulley at point B. And we need to determine the mass of cylinder A in order to keep this assembly in equilibrium in this given position. So because we know the mass of cylinder C, let's start with the free body diagram of cylinder C. I'm going to actually draw it here so that it corresponds to the position of C. So it's subjected to the weight force, which is mc times g, g being the gravitational acceleration, which is 40 times 9.81, and that is 392.4 in the unit of Newton. And also it is subjected to the tension force from the cable, TBC. It's called TB. And we can do a quick equilibrium analysis. So this actually completes the free body diagram of cylinder C. Cylinder C is not subjected to any other forces. So we can apply Newton's first law and do a quick equilibrium analysis. So if we summarize the result, the force along the y direction, positive being up, cylinder C, this equals to TB, positive, minus 392.4 equals to 0. Therefore, TB is 392.4 Newton. And if you draw the free body diagram of the cable BE, so DBC, you realize that we will have a pair of action and reaction. So these two forces are action and reaction. So if the force exerted by the cable to cylinder C is 392.4 Newton, then the force exerted by the cylinder to the cable here is also 392.4 Newton. And there's something else we know about cable. If we have a continuous frictionless cable, then the tension force developed everywhere in the cable is the same, and the direction is always along the orientation of the cable. Therefore, here we will have the same tension force, 392.4 Newton. And this force is action and reaction with this force right here. If we draw the free body diagram of the ring now, this force, these two, are also action and reaction. So this is the force exerted by the cable to the ring, and that is 392.4 Newton. It is at an angle of 30 degrees with the horizon. So let's keep drawing the free body diagram of the ring. It is subjected to this force right here, which is from the cable AE. It is also subjected to this force right here, which is from the cable DE. And this ring is in equilibrium. So from the free body diagram of the ring, so this is a free body diagram of ring at E. From this free body diagram, we can again apply Newton's first law. We can summarize the resultant force along the x direction, positive to be to the right, and that equals to negative TDE plus 392.4 times cosine 30 degree equals to 0. Resultant force along Fy direction up to be positive equals to 392.4 times sine 30 degree minus TAE, and that equals to 0. So we have two equations, two unknowns, TDE and TAE. But in this case, we are not asked to solve for TDE, even though we can actually solve for TDE directly from the first equation, and that's about 340 Newton. But what interests me is to solve for force TAE, because eventually I want to solve for the mass of cylinder A, and TAE, this tension force, is related to the mass or the weight of the cylinder A. So TAE solved from the second equation equals to 196.2 Newton. So now what we've done is we have drawn the free body diagram of cylinder C, we have analyzed the cable CBE, we have drawn the free body diagram of the ring at E. If we draw a free body diagram, a very quick one, of the cable AE, because of action and reaction, this force also equals to TAE, which is 196.2 Newton. So these two forces are also action and reaction. And then it is also subjected to the force exerted from the cylinder A. And this force right here, because of equilibrium, must also equals to 196.2 Newton. So I'm applying first law here again, even though I didn't write it out completely. And lastly, so that's the free body diagram of this cable. And lastly, the free body diagram of the cylinder A. So this is the free body diagram of cylinder A. It is subjected to the weight, which equals to MA, which is unknown, times 9.81. But this force right here is the force exerted by cable AE to cylinder A. And this force right here is also in action and reaction. With this force. Therefore, this force right here equals to 196.2 Newton. Therefore, we apply Newton's first law one last time. Resultant force along the y direction, positive, is up, equals to 196.2 minus MA times 9.81, and this equals to 0. Therefore, from here we can solve for MA, which equals to simply 20 kilogram. And that's the final answer for this problem. So if you look at this problem right here, we applied Newton's first law for equilibrium first time, and then second time, and then we actually applied it for a third time here, even though I didn't write out the equation explicitly, and then fourth time. But we also applied Newton's third law, action and reaction. This is the first time, and then that's between these two, and then second time, that is between these two, and then third time, that's between these two, and lastly the fourth time, that's between these two. Once you understand Newton's first law and third law very well, you can apply these Newton's laws not so explicitly, so you can probably already being able to tell that if the weight of the cylinder is MA times G, then the force at the ring must also be MA times G as well. So you might be able to come to these conclusions pretty fast. However, fundamentally, you need to understand that actually you need to apply Newton's first law and third law multiple times in order to draw that kind of conclusion.